So today we'll be discussing buckling, which is a very exciting topic. And what I want to do is I'm going to consider here. I have here a can of Minute Maid, and this was actually done in the labs, uh, and it was tested. And it was tested for the purposes so that we can learn about what's going on when you buckle. This buckling event that we're going to show you occurs because the cylinder, the cylinder around the can will become unstable if it's empty, if the can is empty. So why we don't go ahead and play the video so you can see what's going on. So you can see there that the can buckled. You can actually predict this buckling event, the load at which this happened in the instrument machine fairly accurately. The second thing I want to point out is if this can was pressurized, like when you buy it new and it's not empty, that means that the buckling load will increase. So the pressure is assisting that behavior really well. Okay. So the can that we showed was loaded on the top edge on the edges with a flat surface. And that was to simulate the potential for compression loading on a cylinder, very similarly to what you will see in an aerospace application. A lot of cylinders that are used in aerospace application, it doesn't have to be a cylinder, it can be a strut, it can be a component like a conical section. Those type of components can buckle when loading is applied. And so the idea there is then to study that a little bit more and really understand how to predict it very well. So in today's lecture, we'll be covering how to do this in actual application, how to predict buckling in actual application. So let's go ahead and so what we're going to do is we're going to share a video here of testing that NASA has been doing to really learn how to optimize its structures. They've taken a pretty large cylinder. The project was called the shell buckling knockdown factor, and this project took place to really update some of their standards, which are used in industry, which is NASA SP 8007. It's not a standard; it's a guidance. NASA SP 8007A came out this year actually, and it was largely based on some of this work that NASA did to really understand aerospace, um, how buckling occurs on cylinders that are used in aerospace applications. So let's watch this video and kind of learn about this.
The test article is a 27.5-foot diameter, 20-foot tall aluminum lithium orthogrid cylinder, very similar to the types of cylinders that we're flying on the Space Shuttle external tank. In fact, this test article is derived from some excess hardware from the Space Shuttle program. So it's configured very much like the future SLS core stage tank structures, so it's very relevant to what NASA is designing today. In this test, we're going to be trying to simulate a lot of the same types of loads that a launch vehicle would be subjected to during flight. That includes internal pressure associated with the fuel tanks, as well as flight loads that you would see, and that would include compression type forces and bending forces, similar to what would happen if you crushed a beverage can under your foot. The black and white polka dot pattern you see on the outside of the test article is used in a system called digital image correlation. And what that system does is we have a series of 22 cameras surrounding this test article, and it's monitoring during the test minute movements of these dots. And from that, calculating the displacements of the test article. It's a really powerful type of technique that allows us to watch displacements of the test article during the test on the entire structure, because traditionally we would only get point measurements, a single gauge here, a single gauge there. For something this large, the digital image correlation system really gives us a lot of good information. The NESC, NASA's Engineering and Safety Center, is the primary sponsor and funder of this project. They saw very early on the need to update these design guidelines, and I came to them with a proposal to form this project, and so they've been the primary funder. The primary stakeholders would be people like SLS, as well as commercial crew, and then industry at large. We have a large following of industry partners that come to workshops, and we discuss a lot of the data and discuss their needs as an industry. So this project, I think, is going to have a large impact in the long term, not just NASA and SLS. Well, we had several visual cues of this thing buckling. We look at data to see that it's buckled. We have our digital image correlation data that's streaming real time for us that indicated, even before buckling was occurring, that the buckling was anticipated. But we can also view the test article outside of our control room window, and we have it positioned in such a way that we can see it buckling at the time. And so it was quite dramatic. We could see it buckle, we heard the bang.
The shell buckling test has been conducted at Marshall Space Flight Center because inside of our load test annex, we've got one of the largest tensile test machines in the world. We've got a movable crosshead that weighs 3 million pounds and can react 30 million pounds of axial compression, making it perfect to do large-scale structural tests. It's an indoor facility, which makes it ideal for the video image correlation systems that we use to monitor real-time strain distributions during actual load events. The space launch system consists of 5 major components: the forward skirt, the liquid oxygen tank, the hydrogen tank, the inner tank, and the engine section. I'm going to be the lead test engineer for the forward skirt and the liquid oxygen tank. One of the biggest examples of how this directly affects the space launch system is we're learning on real hardware that's the same size as, for example, the forward skirt. A matter of fact, the shell buckling test article is the same diameter as the forward skirt, and it's a little bit taller. So we've got a real-life test article that we're practicing on, we're learning, and we're helping provide good data to the NESC.
Lift off.
Okay, so what you guys saw about this, about here, these are orthogrid stiffened shell structures. So this orthogrid provides additional support to the skin wall. Without this will even buckle much faster. When I talk about pocket buckling, what I'm talking about is buckling of these pockets here that's surrounded by these ribs that you see. We call these ribs, the things that are protruding out, and we call this a skin. So yeah, so this is a orthogrid system, structural system, and in general, buckling of these structures can be quite complex. And so this testing help validate some of these analytical models that are going to be used in the next generation launch vehicles. So buckling, what is buckling? Buckling is a structural failure due to excessive displacements. And it's really loss of structural stiffness due to imposed loads. Buckling the process. The buckling process is such that the structure is subjected to loads. The structure can no longer withstand those loads with original geometry, and the structure changes shape to find a new equilibrium configuration. There's possible outcomes that come out of that. So the structure displaces a lot. There's large deflections that could induce plasticity or failure, and structure may or may not be catastrophic. But in general, what is really amazing about buckling, and if you think about it, is that if I have a good predictive model, I don't have to go necessarily to the lab. As long as the analysis technique is validated, I don't have to go to the lab to basically do materials testing, because the buckling event is going to occur and it's an eigenvalue problem, as I will discuss later. So it's a mathematical problem that somehow nature can replicate. We can replicate that with nature. You may not know this, but cicadas, which are insects in the wild, they come out in prime number years. And they come out and they'll mate. And the mating sound that they make is they take the ribs in their back and they buckle it back and forth. And the ribs are in the shape of an arch. And that buckling of the arch in their backs is what's causing the noise. And they do that at high speed. So we see buckling even in nature. Typical regulations. The structure must be able to support limit loads without detrimental permanent deformation at any loads up to limit load, and the deformation may not interfere with safe operation. Local buckling is admissible if it is safe and below the yield limit. The structure must be able to support ultimate loads without failure for at least 3 seconds. Typically, that's what the regulation may look like, except local failures or structural instabilities between limit and ultimate load are acceptable. Only the structure can sustain the required ultimate load for at least 3 seconds. Local buckling is usually admissible if it is safe. In other words, here in this test, over here, about this time, you start to see some pocket buckling before that, right? So if there's buckling in this little pocket, I'm not too worried
that
because it's
indicated,
local.
even before buckling was
Okay.
occurring, that
And those are usually acceptable. The problem is when you have multiple pockets buckling, and now all those pockets buckling together cause the whole wall to collapse. That could be a problem. So that a third typical regulation you're going to see is that when you apply a loading to a structure, a pressure vessel, for example, you don't apply the factor of safety on the loads that cause the structure to be more stable. For example, pressure, the pressure helps buckling not to occur, right? That makes sense. If you have a Minute Maid can, like I showed, and that Minute Maid can was pressurized, when I compress it, I don't expect, I expect that to take a higher buckling load than if it had no liquid inside. So as a consequence, what I'm saying is if I have a factor safety that needs to be applied, I will apply it to those loads that cause buckling to occur, that cause the instability. In this case, it's a compression load. And you apply only a factor of 1.0 on the load that has to do with pressure, because you only want to penalize those loads that cause a failure, not the ones that help you. So that's how you'll do an assessment of that you need to keep into account in your heads as you work through this. So background, thin wall sections composed of either metallic or composite materials are commonly used in the design of aircraft structures and launch vehicles. Thin sections are prone to buckling rather than material failures, and under compression, buckling becomes important. The buckling behavior of a thin wall column is a function of its length. So the longer you have, the more easily it's going to be, you'll be able to buckle it more. The cross section will translate, rotate, and maintain their shape. Now, a long column or global buckling is represented by the classical Euler formula. You've seen that in mechanics of materials. And as such, columns do not exhibit significant post-buckling capability. However, when you look at a very short column, the initial buckling will consist of short waves, with the corners of the cross-section remaining straight. So this type of buckling is really called local buckling and depends on the geometry. And those sections will exhibit a lot of post-buckling capability. The Johnson-Euler curve, people use it to really try to understand the buckling behavior. So in buckling, you're going to have a particular structural layout dimension and what things drive it. So for example, in an aircraft design, I will have the distance between the ribs and the fuselage frames. So what's going to cause the buckling there is going to be the primary buckling of the panels is what's going to drive it. If you have distance between stringers, then local buckling of skin between stringers is the driving factor. Distance between spar web stiffeners will be buckling of the spar web under shear loads, and distance between rivets in an aircraft application in longitudinal joints that'll be driving the local buckling of skin between rivets. So very, very interesting there. Here's, I grew up in Puerto Rico. So here you can see Hurricane George, 1998, causing damage to this water tank. And you can see here the wind caused it to buckle on the side. So hopefully that picture is clear there. Um, in addition, in addition to that, you can see a launch vehicle has collapsed here due to buckling and another one down here. Here you can see an aircraft with buckling, skin buckling. You can see some skin buckling there. But this skin buckling may not have been detrimental, so it may have been acceptable. Here you can see a 757 with had panel shear buckling. In aircraft application, you get panel shear buckling because you have the circumferential ribs, stiffening elements that will react some shear. And so the panel will take shear loading, and the panel you can see here has wrinkled. And this, in this case, it was deemed safe to fly, but it had to be, they had to replace the panels later. In this picture, you can see here some buckling as well. United Aircraft, you can see some buckling there as well. Here is a business jet Hawker 800 XP, some shear bucklings being shown here as well. And here you have a military aircraft. And the point I want to make is in the fuel barrier section, you typically have this fuel barrier here in the core that can also really see a lot of shear as well, that could, and it could cause it to buckle. So buckling of an aircraft panel, you're looking here at a panel that looks like this with some longitudinal ribs, and you know, as you increase the load, you have some amount of shortening. So what I mean with shortening, I'm applying a load at either edge in compression, and shortening is how much I'm compressing it. While the load in the y-axis represents the load that I'm applying. And so I apply that load, and as I apply that load, you're going to start seeing some local buckling occurring, and then you're going to start seeing a more global collapse. You can see the load dropping, and then dropping even more. So that we consider collapse, and I'm really simplifying the curve here for your vision, for your view. But yeah, so buckling can be a process. It doesn't have to be sudden. So buckling, global buckling, typically you're going to have axis of structural member changing. In local buckling, the axis of the structural member does not change considerably. So if you take a ruler and you were to buckle it, the axis of that ruler is going to shift quite a bit, right? While if you have local buckling, for example, here you can see that the axis, which is the mid-surface of that panel, has shifted quite a bit. But if you have local buckling, you can see it has not shifted much. The cross-section of the member can remain constant, while in local buckling, the cross-section of the member changes. Global buckling usually leads to a failure of the structure, and local buckling can cause the failure of the structure, but can be acceptable in certain cases. And so the buckling of a more complex structure could include a combination of these two types, and the video played that of that NASA cylinder is one of those complex problems because it has it can have pocket buckling, which is a local buckling, and then more of a global phenomenon. Here in this picture, what you see, again, is a load versus a deflection. And here what we're measuring now is the deflection of the load application. So at that point, how much it moved downwards. And so that's what we're going to be looking at now. And so in this case, you apply a load P, and it starts stable. Nothing's really moving much. It's moving linearly. With load. As the load is increased, this point is moving downwards in a very stable way. But there's a point in time at which you will get some amount of deformation. Now that's nonlinear. And at that point, you're going to start seeing something we call snap through, where if I did this under load control, so I'm applying load and I'm increasing it, I'm increasing the load, to say 50,000 pounds is the limit load. If I increase the load any further, it's going to jump to the next curve here. And that means that that you have had a significant amount of deflection jump from this point to this point. So it went from this point to the bottom. But if you do it in a controlled fashion where somebody's holding that, somehow holding that load, uh, location of load, holding it but pushing it down while holding it, you can then see that the load required to hold it is lowered, right? In real life, most applications is the buckling occurs, and it's going to be a snap through. It's going to jump, and the reason is because most applications, the applications are subject to load control. The loads are driving the phenomena. It's not somebody holding it in place and pushing it uh, in a controlled deflection manner. Okay, so we will call this stable. It's stable under displacement control. However, on the load control, it's unstable because the load is going to jump from one configuration to another. So you can actually determine the stability of what you have looking at global response. In this example of the shear of the panel, clearly the fuselage did not fully collapse. So just by looking at this picture, I believe it was stable and it will have gotten worse, but it didn't get there yet. So with that said, a little more. So going back here, how do I know if local buckling can be bad or not? So I will not like to have local buckling that leads to permanent yielding. That's probably not a good thing because then it can fail due to low cycle fatigue, which we'll be covering later. I would like to know if that local buckling started to propagate. I have a bunch of local buckling everywhere. In this case, I do, for example. But say I had a small local buckling here, but now that propagated more extensively. That could be a problem as well. If the local buckling affects the performance of the part, functional performance of the part, that can be a problem. um, Local buckling can also precipitate global buckling. So we want to make sure as we increase the load in the testing or analysis that by increasing the load, the local buckling events are not too close to the global buckling events, because if that's the case, then now you're hitting it too close, and that can be a problem for the design. So why we don't look at now at a picture of a colleague of mine, a very close friend of mine. He did his PhD on looking at buckling of these sheets that had these slits in them. And what is interesting here is that this buckling, when you compress it uh, under load control, is unstable and is quite unstable. Imperfect. It also depends on the imperfection of that plate. So the more imperfect it is, the lower the buckling capability you have, because you started with something curved that's going to continue to grow in curvature. A cylinder is similar. Cylinder is going to have a significant amount of buckling reduction with more imperfections included in them. So that's an important consideration that I would like you to consider at this moment in time. Buckling basics. Let's look at the basics to remind you of a little bit of mechanics and materials without going into a lot of analyses and things like that. So when I apply a load to a column, and we want to make sure that the cross-sectional area is selected such that the allowable stress that's acting on this part is less than the strength of the material. So that's one important consideration. We want to make sure that deformation falls within specifications so that it's not too big. If it's too big, maybe the functional aspects will get affected. After design calculations, you may discover very well that the column is unstable under loading and that it suddenly becomes sharply curved or it buckles. And so, yeah, you want to look at that. Here's an example of how you would look at um, a model. It's a simple model of two rods and a torsional spring, just a simplified model, just to remind you how this works a little bit. Um, and I don't want to go into extensive detail, but basically, the restoring moment here due to that torsional spring is the spring stiffness, um, right? K, say, times twice this angle change. So it goes from straight to an angle change of twice delta theta. So that's a spring. Uh, you basically have a restoring moment that basically is reacted at this point. because of that torsional spring trying to react this load applied. I also have the destabilizing moment. The destabilizing moment is this load P, and it's going to cause a moment. And you can calculate that by looking at this height here. Uh, I will not do it here, but it's P L over 2 sine delta theta. And if you use small angle approximation, this becomes delta theta, and that's your destabilizing moment. And the column will become unstable. The column is stable if this destabilizing moment is less than the restoring moment. And when I do that calculation, I find that the load uh, before it becomes critical is 4 times the constant of the spring here divided by the length um, of the rod. And so, what is the point I want to make is that you can see how this formula does not depend on the material strength. It's only a pure relation. It only depends on the material properties, modulus, for example, or material constant, and it depends on the geometry, the length in this case. And this is a simplified idea, so you can see what we're talking about. If you assume that a load is applied after perturbation, the system can settle to a new configuration at a finite angle. It can happen. So I can actually calculate a finite angle if I were if I didn't make a small angle approximation. I can actually calculate a finite angle out of this. So that's interesting. Um, if now I look at a actually loaded bar, a beam like that. Now, so that's basically extrapolating this. This is basically saying I have a bunch of torsional springs all along the rod, but now I have it continuous. I have a bunch of springs going here. Well, this is your classical beam theory. You guys have seen beam theory before, mechanics materials. We consider an actually loaded bar in this case, and you can come up with the equations of equilibrium, and I did that here. The equation you get is this one here, second derivative y, which is the deflection of that beam. Y is the deflection of that beam, uh, plus the load applied P divided by the modulus and the moment of inertia, which is a property of the cross section, times y, which is again the deflection of that beam. I can solve for buckling. It will be an eigenvalue problem. It's an eigenvalue problem that you can solve for that. And what you find is that the critical load will be pi squared, which is quite interesting. This pi squared EI over L squared. In fact, if I give any of you a ruler and I ask you to apply loading to that ruler without having to go to the labs to determine when buckling occurs, is going to be quite interesting because just by using this formula and knowing what pi is, which is 3.14, and the modulus is E, and I is inertia, and L is the length, with that information, I can calculate buckling analytically. What is quite impressive to me is that somehow this occurs in nature, and somehow nature knows about pi squared. That to me is quite insane. The second thing that's quite incredible is this came out of an eigenvalue problem. And that's, I'll discuss that a little bit later. So I'll keep moving forward. This I'm trying to point out here is that you can design against the critical stress in the part or buckling. And so there are a certain amount of ratios where yielding is more important and buckling can be more important. So I'll just move on here, but the longer it is compares to the length, the radius, say, um, say I have a cross section is circular, for example, I can, you will see the buckling now starts getting dominated in these regions of longer lengths. But when I compare to the cross section, but when I look at a lower length, then stress can become the part that drives it. So it's important to evaluate both in real life. You can also have eccentric loading where the loading is quite eccentric. That can happen in a lot of applications and it needs to be considered. And so a lot of people look at an equivalent length. So say it started a little bit bent. Well, you can come up with an equivalent length and apply a load that will behave just like the order buckling formula you saw earlier. And so yeah, any amount of uh, eccentricity can be a problem as well. In this case, I'm looking at one free end, the solution for one free end. Here I was looking at a solution for pin situation. Here I'm looking at clamp free situation. You can look at it as eccentricity as well, but That's not the point. The point is that you can actually derive the solution based on the pin-pin condition. Here is an equivalent length if you want to look at various configurations like pinned, quite, a little bit is pin-pin, for example, but here you have pin clamped. And this is keeping the slope fixed, and then the other slope is completely fixed, clamped. So here, it's a classic mechanics and materials book example. You have the length given, E, the modulus given, the load given, the factor of safety is given. And the question is determine the A over B ratio of the two sides to give the most efficient design against buckling and design the most efficient cross section for the columns. It's a very simple solution. We can calculate the buckling in the XY plane. You can calculate the buckling in the XY XZ plane, and you can just use this formula to figure that out. And here I kind of probably made it more complicated than it needed to be, but I was trying to put it in terms of the ratio um, of A over B. That's why that was done. But I don't want to go into the details of this because you can pause it and kind of look at it later. But bottom line is you can actually design it using the buckling formulas I just provided. Yeah, and then from here you just calculate, you apply a factor of safety to the load, and from there calculate where the buckling could occur and what dimensions can actually take you all the way to the buckling load. And here they're using a factor of safety of 2.5. We're going to see later on that for other applications, the factor of safety can be lower than that. This is the idea of the secant formula with eccentric loading. So if you have some amount of eccentricity where the load is somewhat offset from the neutral axis, then this load is going to cause a moment, and that moment is P times E. So not only have this load, I also have this moment applied, which can cause a deflection, out of plane deflection. So the eccentric loading can also be considered, and bending can occur for any non-zero eccentricity. The question becomes that buckling can become excessive when you have a lot of eccentricity. The deflection formula becomes this one, and the maximum deflection you get is this. So you can actually get a deflection formula for this, and you can actually get a solution. P critical is what I discussed earlier, is that same formula. You can actually calculate maximum stress, but we're more considering the buckling aspects. Again, E is eccentricity, P is the load applied, P critical is a buckling, Euler buckling solution corrected for the equivalent length, depending upon the boundary conditions you have. That goes in here, you do this calculation, you get Y. And here is now an eccentric loading calculation, and the secant formula is provided here. And it shows how you can go from the Euler's curve to this regime where things could be driven by stress. And so we've seen this before. It's been covered in other arenas, but I think it was important to kind of remind you what all this is about. So the y-axis here is the load divided by area. The x-axis is the equivalent load, equivalent length divided by the characteristic distance of the cross section. And you can see how the load capability decreases as the length becomes higher. Makes sense. It's easier to buckle. While at lower loads, it may be harder to buckle, but it's maybe easier to yield or fail in yielding. Sample problem 2 is again looking at a very simple problem, a load applied with some eccentricity, and then all we want to do is again apply the formulas and move on here. So inertia needs to be calculated. Typically, the area of the cross section needs to be calculated, and things like that. And in this case, you can use effective length. Is 8 feet here, so it's free fixed. So we know we can use the pin-pinned solution. If I multiply the length by 2, using the effective length formula, that's 16. I can calculate the critical load, that's 62. I know the modulus is given to me. Still is 30 E6. And I know the moment of inertia because I have the geometry that's given to me. So that's fairly simple. And then you can apply the factor of safety and calculate the allowable load, which is 31 kips. And then you can look at eccentricity to see how much eccentricity you're going to have in terms of out of plane deflection. and then you can calculate a maximum normal stress due to that eccentricity. So very, very straightforward. And the design on the centric loading, I already told you about this, but for short columns, yielding is driving it. For longer columns, we're looking at buckling, and is approaching the Euler critical stress from buckling. So that's the bottom line on this picture. Yeah, so back to the point of that we talked about. You're gonna have a transition from buckling to yielding typically about half times this sigma yield for structural steel, for example. And here I'm just showing some typical um, designs of columns under centric loading. I don't want to spend too much time on this. I'm trying to cover the top level concepts at this moment in time. Sample problem 3, we can look at this again. The idea is to evaluate buckling for this. And again, I don't want to go into the details because I think the whole point was to get the top level view. And then here again, you may recall from mechanics of materials that the total stress is the load applied divided by the cross-sectional area plus the bending moment times C, which is the distance between the neutral axis and the outer fiber of the cross-section, divided by the moment of inertia of the cross-section. And so that's your allowable stress. This needs to be less than your allowable stress. And there are some ways to look at an interaction method to combining these two. So let's move to finite elements a little bit now. So if I look at the governing equation that comes out of the mechanics of solid mechanics for a beam that's pinned and fixed here at this end, I get this governing equation. That's what you will get. And this term here is really geometric nonlinear term. It comes from the geometric nonlinear term, and the boundary conditions in this case are very simple. You have the left-hand side, W here, is the out-of-plane deflection. I was using Y earlier, but now I'm using W. E is the modulus, I is the cross-sectional moment of inertia. P is the load applied. I look at the boundary conditions. Here I have W at this end is fixed, so it's clamped, and so therefore there's no slope and there's no deflection out of plane. On this end, I'm applying a load, but there's no deflection because it's pinned, so that's easy. Also, there's no moment at this end. And so that makes W double prime L equals 0 as well. So if I look at the general solution, I pull up a differential equation book, or I go to Mathematica or wolframalpha.com or MATLAB. The general solution for this differential equation is really this one here at the bottom. And you're going to have 4 constants that are unknown. And the reason is because I have a 4th order differential equation. I can then impose these boundary conditions onto this general solution to solve for A0, A1, A2, A3. For example, I can put in here x equals 0, right? And I get that W at 0 is 0. That's my first equation. I get 4 of those. And what happens is that you get a 4x4 matrix multiplied by a column of unknowns, A0, A1, A2, and A3, equals to a column of zeros. That's what we call an eigenvalue problem. And it's an eigenvalue problem if that happens. And the trivial solution is easy. The trivial solution is A0, A1, A2, and A3 are all 0, which means that the beam is not deflecting at all. And that makes sense. One solution is if I apply load to this and this was perfectly straight, that will never buckle. In real life, it will buckle, but because in real life, you have imperfections. That's why. But hopefully that makes sense. It becomes an eigenvalue problem, which can be simplified to a 2x2 matrix. And if you do the math, you will see that it works out that way. And when you do so, you get to this state, and all you have to do is find the determinant of this eigenvalue problem. So I multiply this by that, minus this by that, and I get a non-trivial characteristic equation when you do the work. And you have to solve for the critical load. And when you do, you get a critical load of 20.16 EI divided by L squared. So what you will get out of that is a mode shape with an amplitude that's unknown. So you're not going to know really anything else other than the mode shape, the shape that it took after buckling, and you will also find the critical load. But you may not know how much it moved. Okay, so So crippling versus buckling, very similar to what we talked about in graphical formula, in graphical form. You can see here for very long columns, you get an Euler buckling type situation, and this plotted in slenderness ratio. So the lower you are in the scale, the more short it is compared to the cross section. And you can see as I get smaller, in terms of slenderness ratio, then I get more and more potential for crippling. So in crippling, you're going to have some amount of initial buckling initially, and then there will be some initial damage, and then maximum load, you have all kinds of damage. That's predicted by finite elements. Crippling can be predicted with formulas in the Composite Materials Handbook. You can open it up. If there's a composite system, you can use those formulas. If the composite is isotropic, those formulas simplify to isotropic materials. So very nice thing to look at. Crippling can occur quite a bit, and it's actually a lot of testing goes on for that. If you look at the number of tests that are performed to look at those kind of scenarios, we're talking about over 100 tests to really address crippling and some panel buckling stuff as well. So buckling of plates is a little bit simpler. Plates under uni-axial compression, we can take a look at that. What you see here is, earlier what I was covering was buckling of beams, but here what I'm talking about is buckling of plates. And when it comes to buckling of plates, it's a little bit complicated in the sense that you have to also consider the aspect ratio of that plate. So I could have a very long plate in one direction and short in the other direction. So this A over B becomes important. That edge A and B become important. And so what these curves do, what they're looking at here is the different boundary conditions you can have. You can have a clamped condition. You can have a clamped simply supported condition, a simply supported plate, and a clamped free condition. So that's your A, B, C, and D, which are mapped here at the bottom right. You can see here, and also I also have a simply supported free condition. And you can see here at the bottom right, I have, and the load is always applied in the B direction. You can see here A, B, C, D, and E mapped to these plates. The way you use these curves, you calculate A over B, the aspect ratio for that plate, and then you can calculate KC based on these curves. And so, for example, say I have situation D, which is a free clamp condition, like if it were to be a diving board, and I'm applying a load in compression, I'll say, okay, well, say the aspect ratio. So say this length is 2 times B. So this length is 2 times B. Then this ratio of A over B will be 2. And so I go here to case D, and I calculate KC of being about 1.6. And you see a dash mark as well, because here you can either have all load edges clamped, all loaded edges simply supported. So you have additional boundary conditions that allow you to do sensitivity studies. Now, finally, I can plug in the KC here of 1.6. I know B and I know D, which is the modulus, basically the bending stiffness of a plate, which is 12. Is 12 divided, sorry, is H, I believe is, I have to look it up. But yeah, so the bending stiffness of the plate D is going to be EH cubed, E is the modulus, H is the thickness cubed, all that divided by 12 times 1 minus nu squared. So EH cubed, all that divided by the multiplication of 12 and 1 minus nu squared. So 12 times 1 minus nu squared go in the denominator, in the numerator, EH cubed. So these fully known, because you know the modulus, you know the thickness. Pi is 3.14, and then Kc is just found from these, depending upon the boundary conditions of the problem. You can figure it out. Plates and shear, a little bit more complicated, but same idea. you can plug in K into this formula here at the bottom left. Um, but the idea is that you can predict buckling due to shear loading. Many people may not know, but buckling does occur under shear loading as well. And then here I have a list of variables that are used in the Composite Mill Handbook 17, and it provides a number of expressions that you can use for predicting buckling of a composite plate. And here what you can see is also experimental data being shown, and it's very neat that you can basically use this formula. And here what you see is D11, D22, D12, and D66. These are basically variables, bending stiffnesses of a plate for composites. And so these closed form solutions tend to work very well. And I invite you to take a look at the Mill Handbook for that and kind of go through that. We won't do that here because these are basically handbook formulas you can find. Yeah, so the formulas, there's many of them for different boundary conditions. So yeah, so here you can see solutions for plate, but also for isotropic plates, but also plates are composites, and can be fairly leveraged. Yeah, here's a solution for all basically uniaxial loading and biaxial loading with so basically you have loading in both directions now, and you can see that I can apply a load here that's phi times the load in the other direction. So phi can be varied, and this buckling solution will still work by putting phi in there. And you see a lot of variables here. What you need to do is find m and n to minimize n. That's how that works. D11, D12, DC6, D22. If you haven't taken my composites course, you can take it or watch some of the YouTube videos I have on that. Um, the stiffness matrix for composites is fully known. So these numbers are fully known. You select m and n to be minimizing n. Phi is known because that's the load applied and the ratio of the biaxiality, how much biaxiality you have. For example, phi is 1 if the loading is equal in both directions. So you have that. You know the b over a, like what that is, the ratio of one edge to another edge, and you know pi, and you know b, so you can calculate the critical load. So 30 simple calculation. And then here's another one for plate with loaded edges simply supported and unloaded edges fixed. Crippling shape can take a lot of configurations. So that was more to show you guys that crippling can take a lot of shapes. You can have one mode, multiple modes, things like that. And there's in the composite mill handbooks, there's normalized crippling data for no edges free, for example, and you can use that for your design purposes. And here's more examples from that book, and which I invite you to download and take a look. And it does it for various cross sections. Like here, you have another one. This for one free edge. This for no free edge. Okay, so with that said, let me now cover finite elements. How we go about this in finite elements. We will be looking at that, and you'll be following some of the YouTube videos to kind of complete some of the projects. So I'm going to start over again with how finite element works, right? The way finite element works is that you have a complex partial differential equation, and the partial differential equation needs to be discretized over a domain that can be quite complex. And so the idea there was to divide the domain into subdomains, and in each of those subdomains, I'm going to approximate the solution using simple polynomials that could be either linear or quadratic. And by doing so, what I've done is I've discretized the system so much that I can now turn the problem from partial differential equations over complicated domain to a linear system of equations that can be now solved. When it comes to buckling, what you will often get is a linear buckling analysis, eigenvalue analysis. It's an eigenvalue analysis that needs to be solved. But the idea of proceeding is very similar to what we discussed last week, where in the last lecture, I apologize for, where we take the differential equation multiplied by a function v, and what we try to do is we distribute these derivatives to v by integration by parts, which we're not going to show here because you can pull a calculus book to show how that's done. So just integrate by parts twice here, one time here, and then you get these boundary conditions that come up. And so from there, what you find is that in our problem, um, these boundary conditions completely go away. And the reason is because, for example, in our scenario is pin pin, I believe. So for pin pin beam, the deflection is fixed. So this can be set to zero at x equals zero. At x equals 0 is also pin, so the deflection out of plane is also zero. So this goes away, and so forth. When you apply these boundary conditions, you will see that it works out all to be zero. And so you're left with this simple expression here at the bottom that you see. And again, W is a deflection out of plane, E is a modulus, I is a moment of inertia. V is an arbitrary function I'm using to make this differential equation orthogonal to that function. And that function I'm going to be selecting as a shape functions for that subdomain. That's how finite element works. And again, what I've done is I've taken this equation, multiplied by that function v, and integrate it over the domain. So I get sort of like an average error that I want to really get to zero if I can to make it happen. That's really what I'm doing there. So for this formulation, what's typically used for beams is this type of shape functions are cubic, and they're selected in a smart way to satisfy the conditions you can have at either end of the element. Because the element is a beam, so you're going to have two unknowns at each end. One end is going to be the out of plane deflection, and the other is going to be the slope. Those are the two types of boundary conditions you can have for a beam: fixing the slope or fixing the deflection out of plane. So as a consequence, I have two unknowns at each end of the beam that have discretized, and so therefore I have four different functions I need to approximate the behavior over this element. And so what's typically done is that you use these four shape functions. I select the cubic because I have two unknowns on either end, so that I need, and I have four unknown coefficients, and a cubic polynomial has four unknown coefficients. So this works really well. And so my unknowns are the deflection out of plane, V1, theta 1 is a slope, V2 at node number 2 is the deflection out of plane there, and theta 2 is a rotation at the other end. These are the shape functions I'll be selecting here at the bottom, 4, and they're selected in a manner that satisfies the boundary conditions in a smart way. For example, if I set x equals 0, I'm talking about the beam at the very left, the node at the very left of that beam at x equals 0. You can see if I set x equals 0, N2, N3, and N4 go away completely, and I'm left with deflection of N1 is 1 times V1. So I get exactly what I wanted. So that's how these were selected, to be smart about it. I can now do, as an example to show you how this works, I can set x equals L to see what will happen. When I do that here, you'll see that there is 0 at x equals L. This will be 0 at x equals L. This will be 0 at x equals L. But this one here will survive, and it will give me 1 again. Beautiful. N3 is 1. So this is 0, this is 0, this is 0. When I multiply this to this, I get the deflection on the right-hand side is exactly V2, which corresponds to the N3 that was a 1. The slopes, again, I take the derivative of W prime, so I have N prime, N2 prime, N3 prime, N4 prime. And when I set it x equals 0, you will see that I will get the rotations now instead. So this is how these functions were selected, is so to make that happen, right? So we've approximated the behavior within the beam. I put this in matrix notation, n times d bold. D bold contains the unknowns of that beam, which are the deflections and the rotations. And yeah, so I'll use that. Oh, and I had the picture here, I'm sorry. So this is the beam, and these are the node number 1, node number 2. Remember, every element is going to have nodes that describe the domain, the subdomain. And here, the nodes for beam are here and here. So yeah, so I want to solve for those nodes, the values at those nodes. And so the idea then was to then plug in W for this approximation n times D, which is this multiplication. And then for anywhere I see V, I'll substitute by n transpose. And when I plug it in, I get this equation here at the bottom, which is an eigenvalue problem. All these will be numbers, by the way. All these will be full numbers. P will be the only thing that's unknown, and D is the also unknown. So you do get an eigenvalue problem on P alone, which you can then use. You can find the determinant of this matrix to find the solution. And I've done that here. I've calculated what these things look like when you multiply everything out. You know, I don't want to confuse you. This is very easy to do. You plug all this in here, and is when you integrate a mathematic or MATLAB, this is going to spit out numbers, these matrices. And P is not known. The length is known of the beam. These are unknown. So now what I need to do is to go ahead and apply the boundary conditions. In our scenario, if it's pinned, the deflections at either side are zero. So I'm left with the second row and third row has been important. And when I find the determinant of a 2 by 2, basically, for one element solution, just one element, I get a buckling value of 9.69, and the closed form solution is 9.86. So it's incredible I can get the answer with a single beam, which is incredible. If I look at higher level modes, you can get buckling with higher level modes, then it will be way off. But I need to increase the number of elements for that. In Abacus, the way it works for a linear buckling solution is you will invoke the start buckle command. So if you do this, it will extract the first, and I put 2 there, it's going to extract the first 2 buckling loads. So that's how it works. And to remind you how Abacus works, you can do it by hand, all this coding, and run it in Abacus. The first section of Abacus is going to define the nodes of the element. I'm going to do a single element. Then I'm going to define the element type. And this element type means I have 2 nodes, basically, and this is a 3-dimensional beam. It can be. And in this case, this element number 1 has nodes 1 and 2, which have these coordinates with those nodes. So that's what that means. The beam section was selected as rectangular, and the material aluminum. And the material here is explained very well. You can see here I'm providing and it's a rectangular cross section, and these are the dimensions of the rectangular cross section. The material is aluminum, which has a modulus of 10E6 and a Poisson ratio of 0.33. We're making a pinned on one end, and the other end we're making a roller, and we'll apply the load on the roller side. And you can see I put start buckle, get the first 2 modes, and then apply a load in that rotor, a concentrated load. And when you do it, you're going to find you'll be very excited to see you get 9.69 compared to the final elements, but doing by hand. So Abacus is doing it correctly, obviously, because, well, we're doing it correctly, but I think they're doing it correctly because we're the ones who are right, and they're copying us. But regardless, you follow what I'm saying. You can also look at the effects of geometric imperfection. We can continue. We can look at effects of geometric imperfection. You can put a little imperfection here of, this amount. Everything is going to have imperfection in real life. And you can solve the equations, and I already covered it. When you solve it, you get the deflection. And you're going to see that the deflection is going to increase the more imperfection you have. So something to know about. So let's look at buckling of shells. Actually, let me step back a little bit to make sure it's clear. So as P approaches P critical, the buckling load that for the straight section, if everything was straight, right? If I calculate a buckling load, the deflection can go into infinity, okay? But the important thing is that if the load was not close to P critical, I can actually calculate finite deflection for an imperfect beam using this formula here. But Abagus can do that for you. Let's look at buckling of shells because a lot of aerospace applications have that. So here's a shell torsion buckling. You can see here a curve comparing the test and theory for the buckling monocoque of cylindrical shells on the torsion. Here is Z is called the Bar-Toff parameter, which is really nothing more than this equation here. L is the length of the shell, A is the radius of the shell, H is the thickness of the wall, and you also have nu, which is a Poisson ratio. On the y-axis, what I'm showing here is a shear buckling coefficient, which is multiplying a sigma critical. And the idea there is that, or tau critical, which is a buckling stress. And that came straight from this reference here, AIAA Journal, Volume 19, number 9, 1981. You can calculate the shear buckling coefficient factor that's used then in the design. So that's how these curves typically work. You know these values, you can calculate the shear buckling coefficient that's then used in a formula to predict buckling. So shell buckling, linear buckling solution for shells can be determined using procedures available in Abagus. That's not a problem. Cylindrical shells buckle linear, elastically, unstably, and is initiated by geometric imperfections. Let me repeat that one more time so it's clear. Cylindrical shells buckle linear, elastically, unstable, and initiated by geometric imperfections. They can first start in like a linear elastic buckling, but they can turn into plastic deformation. Thickness variations out of round conditions and lateral loads need to be considered in these assessments. Here you see shell buckling. A buckled, uniformly axially compressed monocoque cylindrical shell with a large radius and thickness. You can see here that's buckled quite a bit. Now you can see that the post-buckling looks quite interesting, and the reason it has this pattern is because for instead of the whole thing collapsing suddenly, what they did is that in the inside they put a mandrel of slightly smaller uh, diameter, so that when this buckle, it will hit that mandrel, and so that's what you see there. So cool picture of buckling. Here you can see buckling of an actually compressed, actually stiffened cylindrical shell. And the buckles are quite large, and the reason is because there is a large effective axial bending stiffness of the stringer stiffened wall. This behavior really greatly reduces imperfection sensitivity. So is really imperfection sensitivity is that cause really a big reduction in buckling compared to analytical solutions. What happens is that the experiments, okay, so everything I showed before with this stuff, uh, analysis predicts very well. That's the bottom line. When you move to cylinders, analysis does not do very well because the analysis doesn't have the imperfections, and cylinders tend to be uh, imperfection sensitive. As a consequence, because shells tend to be imperfection sensitive, the more imperfection you have, the more you're going to be off in terms of analysis correlating to test. And so when you have these large axial bending stiffnesses with a stringer stiffened wall, the effect of imperfections decreases. So you won't have, these small little, divots that form after buckling. And so if you have imperfections that look like this, these are small, you're going to have a large reduction in how analysis compares to test. Analysis will always overpredict buckling for shells, but that's because of the inability to include imperfections. But I'll show you that there is a way to include imperfections, and you'll be doing some of that. Here's shell buckling of a sphere. You can see here is uniformly externally loaded. They did the same thing where they put a smaller mandrel inside to prevent the whole thing to buckle apart. And they stabilized it artificially with that approach. And beautiful picture of buckling there. Here you can see buckling also of a ring stiffened cylindrical drum, basically. And yeah, so just several pictures of that. I think it's quite interesting to see this one right here, where you see a buckle that's quite significant, running long, lightly stiffened cylinder looks like this. It's more of a general buckling. When you have this scenario here, you can see it's buckled locally there. That usually happens when you have a heavily stiffened uh, cylinder. You get quite a bit of plastic buckling. On here, you have a moderately stiffened panel or cylinder, and then you get local buckling between the rings, but nothing as dramatic as this one, and this one is more local, more global buckling, if you will. Here you can see shear buckling. You can see wrinkles in the cylinder due to that. And then you're going to find that there is also an imperfection sensitivity for those designs. So let's hit the point. The bottom line here is when you do a linear buckling solution for cylinder in axial compression, it usually compares well with finite elements. That's a good news. So, so this solution that was done by hand usually matches finite elements. That's a good news. And E is the modulus, nu is the Poisson ratio, T is the thickness of the wall squared, R is the radius. And this is a line load here. Um, and so, yeah, that's going to match pretty well if you do it either way. You can see that the buckling modes tend to be quite localized. So this is your linear buckling solution. The problem is that the linear buckling solution, as opposed to the other examples again of a beam, don't quite always match test data. And I'll ask you this, so does the analytical solution compare well with experimental data? And the answer to that is it rarely achieves the actual design. And the reason for that is due to geometric imperfection. Analysis usually does not match test because of geometric imperfections. And to show you that evidence, what was done here, the ratio, so if you took nu of 0.33, I believe, and you multiply all this stuff out, you're going to get 0.605 EH divided by A. Okay? And I'm using different parameters here. A is the radius, um, H is the thickness, E is the modulus, and the buckling stress, what's shown here is the buckling stress, measured experimentally divided by the analytical solution, which is this one. And the reason you don't see T squared is because there's a single H there you can see, is because this is a line load. So line load divided by T gives you exactly the buckling stress here, the analytical solution. So if I take the experiment and divide it by analytical solution, if it's 1, it will be perfect. So the analysis matches test, right? If it does 1. But when you do the test, you find that your analysis, when I do this plot, the analysis is off. And so there is a NASA standard 8007 and now NASA standard 8007 A, and it's not a standard, it's an SP document, a guidance document. It provides some insight into this test data. And the bottom line is that there is a difference between analysis and test. It doesn't match, okay? So yeah, this is the ratio of the experimental buckling stress divided by the one predicted by analysis. And it's going to match finite elements if you ran it. I guarantee you that. This formula looks slightly different from this one here in the denominator. And again, I want to explain the reason one more time. I believe nu was assumed to be 0.3 or 0.33. So that turns this into a 0.605, that coefficient. And then finally, you'll see that this T squared, which is the thickness of the wall, while here I was using H for the wall thickness, you can see squared here, but not here. The reason is because it's a line load. If you divide line load by T, you get stress, units of stress. So that shows that if this experiment matches analysis, you will have been up here, close to 1. But because then the experiments were so low compared to analysis, the value is lower than 1 by, as the radius to thickness increases, that value is decreasing, you can see. Okay? And so the design recommendation that was given was that, hey, you have a lot of scatter in this data. And so, and that why is that? Because every cylinder is going to have a lot of, every cylinder you manufacture could have a lot of build-to-build variability, right? Not every cylinder has the same imperfection. And so that's why you see the scatter show up. Now the manufacturing has improved, and we're going to take advantage of that coming up. But in initial design, you want to use this initially. So in other words, I don't want to hit this point again, but this recommendation came from this journal here and is now used quite extensively in the industry. So here's another picture, another view of that, experimental divided by analytical. You can see again, if it was close to 1, no problem. But as you go higher and higher up, you get a lot of scatter and the knockdown factor increases. And the high dispersions you see are due to the variability in geometric imperfection data. Yeah, so one question is very natural that comes to your mind is, why will you use a curve that's this aggressive if we can do better? And the answer is, at the beginning of your design, a preliminary design review, or at the beginning of everything, you don't have a good idea of how well you'll be able to manufacture, cylinders, they're close to perfection. And so for initial design, I think this is very helpful to get started, and then refine, do your pencil sharpening down the road by including more advanced analysis approaches. So moving forward here, then the shell buckling coefficient is shown here. I already covered that one, um, and so let's look at what's going on here. Here's the linear buckling solutions for axial loading on the left side, and then on the right side I have the one for torsion. And here's the documents that NASA has for predicting buckling for various structures. 8007 became available. It's 8007A now, and is available. So you can start looking at that. Moving forward here, so how you use this information, how you design something like this. So we can start with the margin of safety. So um, this right here is the critical load when buckling occurs, and these are associated mode shapes. Okay. So let's look at this document. This is 8007 new revision 2020. I call it A, but it's incorrect. It's 2020. And the way you can use this information has a table of contents, has a brief history of the shell buckling research and the previous NASA design criteria, and it provides the factors influencing the buckling of thin wall cylinders. It provides effects and design concepts, features. It provides analysis methods, how you can analyze this stuff, design approaches, and empirical design approaches that you can use. And then it goes into analysis-based approaches, which really help with deriving this factor that I'm going to call knockdown factor, and I'll explain what that is. And you can see here some of the original test data shown here that kind of demonstrated that reduction from experiments to analysis. Experiments lower than analysis by quite a bit. And you can see here the 0.06 multiplier that we were talking about earlier. So yeah, this handbook is used extensively in the industry for predicting buckling, and it's been revised, and that's why I thought I'll share with you that. So for initial design stages, you're going to use the eigenvalue that comes out of Abagus, or you're going to just use the closed form solution, whatever is feasible. Gamma axial here is a knockdown factor. What I mean with that, so you go here to this curve and say, okay, R is 60, T, or it says 50, T is 0.01, or say it's 0.1. So 50 divided by 0.1 is 500. So I'll go here, select 500, and get a knockdown factor of 0.33 or so. So that 0.33 gets multiplied to this eigenvalue that was predicted by analysis. In other words, I was so off, I had to multiply by 0.33 to get it back in line to testing. But not all testing, right? Because you can see here that there's a lot of scatter. Even at 500, I could be even as good as 0.6. So 0.33 is the minimum design curve that was decided back in the day. So that is approach number one. You should take the knockdown factor. You're going to have the eigenvalue. So you're going to apply, the first step is to apply the limit load to the model. So you're going to apply, say, the limit load. What is limit load? So limit load is a maximum load the part is going to experience in service, and usually statistically derived. So it's a maximum value, usually the +3 sigma type load, 9990 enclosure. And that load is the maximum load you will see in service. So say a cylinder for a launch vehicle application is going to see 1,000,000 pounds. And that's a limit load that's going to be seen. You can apply that to the model. And that load applied to the model will produce an eigenvalue. That eigenvalue, what it tells you is how far off you really are from buckling. So for example, if you got a lambda you found a lambda, the buckling load, the buckling factor, right? The eigenvalue, the buckling eigenvalue was, say, 0.5. Then you know that the buckling load will be 1,000,000 pounds that you applied times 0.5, which is 500,000 pounds of load. So that's your buckling load. So in other words, lambda times kf, lambda times kf, the knockdown, not lambda times kf, I'm sorry guys. Lambda times the load that you applied is going to be your buckling load. That's what that is. So uh, just wanted to explain that idea of lambda here. So again, one more time, you apply a limit load to the model, and the limit load to the model will produce an eigenvalue. The eigenvalue multiplied by the limit load will provide the buckling load, the total buckling load. But in reality, when you do the margin calculation, I want to show you something. If I multiply P here, P times the eigenvalue, lambda, at the denominator, I'll also apply P times factor of safety. So P and P cancel. So the million pounds you applied in the model never show up because it cancels the numerator and the denominator. So all you need is really to apply the limit load into the model, the maximum load into your model. You get the eigenvalue, take the eigenvalue, multiply by the knockdown factor, which depends upon the R over T ratio. You plug it in here, you divide it by the factor of safety, minus 1 gives you the margin of safety. One more time. You apply the limit load to the model, times the eigenvalue you calculate, times the factor, the knockdown factor, which gives you the difference between analysis and test, how off you're going to be. So that comes from this curve, divided by factor of safety minus 1. Another approach is to apply a value of load 1 into the model. Just apply 1 pound into the model. So then, or don't even worry about that. Just apply any load you want into the model. Then that's going to produce an eigenvalue. So take that load you apply to the model times lambda, right, will give you the critical load for buckling times the knockdown factor that I talked about. Divide that by the limit load times the factor of safety, minus 1. So that's another way to do it. But I think this is the simplest way. Apply the limit load to the model, get the eigenvalue, multiply it by the knockdown factor, which gives you the difference between experiments and analyses, divided by factor of safety minus 1. And this approach tends to be conservative. It tends to be. Okay? So with this approach,
Yeah.
we're not applying imperfections.
Yeah.
With this approach, we're taking a cylinder with no imperfections. So in the finite element model, it will be a perfect cylinder. And then you apply that loading in compression. That's going to cause it to buckle. That's going to be overstated. That's going to be overstated. And so therefore, that's why you have to adjust it down using this knockdown factor so it can then bound what has been observed in experiments. Okay, does that make sense? Yeah, very nice. I'll be discussing that in approach number 2. I'll discuss an approach that is less conservative than this, but is more complicated. And I'll cover that in a minute. So let's move to an ISO grid design handbook. So there's a handbook that actually provides, and that's NASA CR 124075, that provides a number of formulas for predicting buckling. And it provides the source for those. So that's something you guys can look at. I'm not going to spend a lot of time on this particular page. So let's look at an example of a cylinder on the axial loading. I model a cylinder. I apply a load on either end, and we want to determine the buckling loads using the eigenvalue extraction procedure in Abagus. In Abagus, you can do all this potentially in the GUI, but if you want to look at what the GUI says, I think it's worth kind of looking at it real quick, the code. You define all these nodes, the coordinates, and I put 3 dots here because I don't want to show you every single line. This model has 8,000 nodes, but every single one of these nodes has an XYZ provided, the coordinates. XYZ is provided fully here. And then after that, I have selected an element, and the type selected here is S4R, which is a shell element. Okay, it's a reduced integration. I don't recommend reduced integration, just use full integration. So use a shell for S4. And what you see here is the element number 1, 2, 3, 4, 5, blah, blah, blah. And what this is it tells you that element number 1 is made up of nodes 1, 2, 52, and 51, whose coordinates are given in the previous part of this code. And so if I were to select element number 1, perhaps it's this one right here, I should be able to tell that that element is made up of these 4 nodes. and the element label is 1. So that's how it works. And then the shell section is basically defining, the thickness. Here, I don't know if the thickness was 2. It sounds pretty large. It may have been a different, it could have been a different unit system, potentially. I do not know right now. But you'll have a shell section that defines the section properties of those elements. In this case, we're calling aluminum, and here's where you'll specify the thickness. And then you'll go and perform a linear, and then you'll define the material properties for aluminum. I showed you how to do that earlier. It's the same thing, copy and paste here. And then you'll perform a linear buckling solution, and you'll type buckle, and this should give you 3 buckling modes. The first 3, and here what you're doing is you're applying the boundary conditions on how these points should behave, and then whether it's clamped, simply support, or whatever. And then you apply, here a unit load was applied, which means the eigenvalue that's going to come out is the buckling load. That's what will come out. In this case, we assume the limit load is 425,000 pounds of unit load. And when we apply that load, the maximum load, the eigenvalue was determined to be 1.147. So then the buckling load, it becomes 425,000 times 1.147. That goes in the numerator here. Okay. I think there could be, I'm sorry, it's 1.147 million units of load, right? So that's what that is here. Times 0.0, so that's your buckling load, 1.147 that, okay? So in the model, we did not apply 425,000 pounds. What was applied to the model was 1 pound, and that gave an eigenvalue of 1 million pounds that's here in the numerator. Times 0.54, which is a knockdown factor. So if you look at our problem, which I didn't give the dimensions, but if you look at this curve, the R over T was close to this number, 0.54, 0.55. And so I'll put 0.54 there. And the factor safety is 1.5. The load, the limit load is 425,000 pounds. Alternatively, you could have applied 425,000 pounds to the model and get an eigenvalue. And then all you had to do in that case is take the eigenvalue, multiply by 0.54, and divide it by 1.5. You don't have to put these numbers in there. But this gives you a margin minus 0.03, and that probably requires a slight redesign. Not a big one, but slight one. Okay, so let's move to another approach that's less conservative. And the idea then is actually to put the imperfections into the model. And how do I do that? So you're going to rerun an analysis now using the same model you have. But now what you're going to do, you're going to import what we're going to claim. We're going to make a big claim. We're going to claim that when you do the linear buckling analysis, Abagus will produce these mode shapes. We're going to claim that if the mode shapes happen to be the imperfections that we have, it should be much easier to buckle if the mode shapes were of that kind. And so the idea then is, let's go ahead and incorporate those mode shapes into the model. And here what I've done, I've selected 3 modes, and I've amplified the mode shapes by 0.2, 0.1, and 0.05 as an example. And this could have been selected based on the manufacturing. Like, you know that it's not going to be worse than that amplitude of imperfection. Remember, you can take any mode shape and scale it up to whatever number you want. So what you're really doing is you're starting with a new model, a new clean slate model, And what Abagus is doing in that step is taking all these nodes and moving them circumferentially. And it's moving it to match the mode shapes corresponding to the buckling modes that came out of this model, this eigenvalue model. Once you do that, you're going to run an analysis that's nonlinear. It's highly nonlinear analysis. You need to put here nonlinear geometry equals yes, because it will be large deformation analysis. And then you put a Rick's procedure, which I don't want to get to that in this class necessarily, but allows you to track the equilibrium state of that cylinder. It allows you to do some complicated things there. And then you're going to apply, in this case, I applied a load of 1,000,000 pounds, but you can apply whatever you want, like I said before. And typically, what you want to do is when you apply the imperfections, you want to get them out of what you expect from production, right? Which should be better than when these curves were generated. And that's what you will see also in the NASA SP 2020. You will see that explained. So the next step is to apply the load, rerun the model, but now non-linearly. And now the analysis is not going to produce an eigenvalue. It's going to produce a curve with meaningful deflections. And you're going to track the deflection at the point where you think things are happening. So you can see here already some things are happening here. And it seems to have the appearance of these things growing over time. So you're going to track one of those dots, one of those locations, and then track it. And what you're going to see is that as you apply that load factor, as you apply the load, the maximum displacement of buckling at that point is going to start going out of control. So you can see here about this load factor, the maximum displacement at buckling is going out of bounds. It's going crazy. That means that buckling is going to occur about there. And so you're gonna plot this. Abagus allows you to plot the load, this load factor, and as a function of that deflection, you can actually do that. So when you do that, you can actually then figure out where that buckling is occurring. And you may ask me when the buckling occurs. Well, I applied 1,000,000 pounds, so 0.4 million pounds is about 0.42. So that's when buckling is happening at 420,000 pounds. So then I go here and I write a margin of safety. And when I do that, I get a margin of safety that's actually quite negative. And you may ask me why. So I thought earlier I said it should be more conservative. I think not necessarily. So in most cases, yes, but it's possible that this design that I'm talking about, these imperfections were worse than the test data that was gathered. So what you want to make sure is that whatever imperfections you have in your manufacturing, that they're bounded by the testing that was done back in the day, if you want to use these curves. But most likely it should be more benign, and you should expect these numbers to be way lower. So that's something to keep in mind as you do this. So in this case, the design is not adequate, and the cylinder should be thickened to avoid negative margins. Another approach is to try to figure out how to improve the production so that the production is more repeatable and that you're not getting these large imperfections to begin with, like a dent, a ding, or an out of run situation that could be quite important to address. So let me show you the different approaches here one more time. And, you perform a linear buckling analysis. You extract the buckling load and the eigenvalue, the mode shape. Approach one is to take that knockdown factor from the handbook, take this buckling value, and calculate the margin of safety. That's approach number one right there. Approach number two is to go ahead and now take the hardware measurements, scale the eigenvalue, eigenvector to bound measurements of the of what we saw. Then you perform a nonlinear analysis like the one I showed here, using the Rick's method with the nonlinear geometry of yes. And then you will then identify the buckling load by numerically looking at the data. You're going to start seeing some weird stuff happening when you track a single node that's in an area of buckling. And then from there, you can then calculate a new knockdown factor numerically, which can then be plugged into this margin of safety calculation. So two approaches been discussed here. A here is the eigenvalue, and here A star is the one that you calculated non-linearly. So that's what that is. So that's how that works. Yeah, so the mode shapes are typically scaled to 1. And so that means that any multiplier to the mode shape of that's a scalar to 1 becomes the actual imperfection amplitude. So if you have drawing tolerances that say that out of round imperfections cannot be greater than 5 mils or 0.005 inch, then you already know that all you have to do is come here and put 0.005. If you know that after they manufactured, even with that drawing tolerance of 0.005, somebody came in and hit it with a hammer without realizing it. And now that amplitude is 0.2 inches. Voila. I take the mode shape which is scaled to 1, and multiply by 0.2 by adding this start imperfection um, uh, 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 command that the Abagus allows you to do. I do want to conclude today's lecture by covering some design formulas really quick. This comes from the Rourke's Stress Handbook. And so I do advise, if you're going to work in this area of expertise, download that uh, through the library or through your industry partner that you work for. And it's really good. It's very beneficial. It has plates under biaxial compression, has plates under non-uniform loading, for example, has loading in one direction alone, with different boundary conditions as well, with a K factor provided. It has shear loading as well, shear loading conditions, and closed form solutions for cylinders, as the one I discussed. This formula is exactly what I showed you earlier. In fact, if you look at this and look at what I have, it's the same thing. And then you see here torsional for shear. If you apply torsion to cylinder, you'll get shear buckles. You can see here pressure, a cylinder under pressure, hydrostatic pressure, and a solution for conical sections as well. And these formulas can be very useful for initial design. And then what you want to do is apply a knockdown factor that comes from these NASA standards for the initial design phases. Once you get smarter about the manufacturing, you can start using these nonlinear analysis tools to kind of refine and remove weight if you can. Another approach is if you have experience from heritage that tells you, you're likely not going to have large imperfections. You can try to use some of that data to kind of guide that process, and you may not be able to bank on it 100%. You're taking a risk there that you may not be able to manufacture it that accurately. But overall, it's an approach that works really well. And so to me, buckling is a very interesting topic because it occurs it needs to be designed against, and it is a very strange phenomena. It's a strange phenomena because for certain cases, it's an eigenvalue problem that somehow you can actually predict, and nature somehow has memorized its eigenvalue. It's interesting that occurs. It's interesting. No, I don't think there's another area of expertise except for dynamics where um, the nature, mathematics, however this world works, these things happen naturally, but I can predict them in a way that's quite incredible. With that said, I thank you for attending this long lecture on buckling, and I will be talking to you soon next time about a different topic.